Welcome back, Virtual Precalculus. So, we've talked about imaginary numbers or complex numbers before, and we've always expressed them in terms of what's called rectangular form. A form like this, a plus bi, where a is the real part and b times I is the imaginary part. I'm not sure, I can't remember if we've talked about already how to plot these things, how to graph them. But the way you do it is you graph them in a place called the complex plane. It looks just like the normal xy plane that you're used to. And the coordinates of the point that we would plot for the number a plus bi would be a comma b. So for example, 1 minus 4i would be 1 comma negative 4, 2 plus 3i, 2 comma 3, etc. And you can see in this graph here I've shown 4 points like that just to give you an idea of how this works. So if you need to, pause it for a second and think about how I figured out where to put all of those. So once again, this is known as rectangular form, where we specify the location of a point along the real and imaginary axes, in effect giving them an x and a y to find their position in 2 dimensions. Well, another way to find the position of something in 2 dimensions is in what's called polar form. Instead of specifying x and y, you can specify the distance of the point from the origin and the angle. And if you look at this little diagram here, you can see what I mean. That same green point from above, 2 plus 3i, we can think about it instead of moving over 2 and up 3, we can think about, well, how far from the origin do we move and in what direction? Well, we know how to find that r. We can just use Pythagoras and imagine a right triangle. Then r has to be the square root of 13. Right, and the notation we use for that when working with these kinds of complex numbers is that is the modulus of the number 2 plus 3i. And we use these absolute value looking bars to specify that. Here's a formula that works in general. The modulus of any complex number a plus bi is just the square root of a squared plus b squared. So continuing with this same example, this number 2 plus 3i, we found the modulus, or the distance from the origin, but in what direction is this number? What is the angle theta? Well, that's not too hard either. We can just use right angle trigonometry to figure out that the sine of theta is 3 over r and that the cosine of theta is 2 over r. So that's 3 over root 13 and 2 over root 13. Because the sine and the cosine are both positive numbers, we know that this thing must be in the first quadrant. And when we use inverse sine or inverse cosine, it's up to us, we find the angle. Theta is 0.983 radians. Okay, so in general, these equations down here will work for any complex number. To find the angle, we can use the fact that sine theta is b over r, where b is the coefficient of the imaginary part, and cosine of theta is a over r, where a is the real part. Once again, r is the modulus, or the length of the radius connecting the origin to our point. Up here at the top, you see that putting it all together, our number 2 plus 3i can be expressed in what's called polar form as the square root of 13 times big bracket cosine of 0.983 plus I times the sine of 0.983. Okay? Here's another example. Example 2 from your text in section 10.1. Let's change negative root 3 plus I into polar form. Well, let's identify a and b. A is negative root 3, b is 1 because it's 1i. Okay, a and b are never going to contain the I themselves. The I is not part of b. Using that, we can find r, as you see here. It's got to be 2. And using our formulas for cosine and sine of theta in this situation, we find them to be negative root 3 over 2 and 1/2 respectively. That places us in quadrant 2, and so theta must be 5 pi over 6. And here you see the full number written in polar form. Alright, so now that we have this new form at our disposal, it turns out that there's an easier way to multiply and divide complex numbers. If they're in polar form, then multiplying them and dividing them is a cinch. Let me show you how it works. Let's say we have these two numbers z1 and z2, and they're expressed in polar form. You see there's the modulus of z1 and the modulus of z2. The moduli is the plural way to describe them. And here's the angle for z1, theta 1, and the angle for z2, theta 2. Now if we multiply these things together, well, r1 times r2, we can put that out front. We can multiply factors in any order we choose. And then we have this horrible foiling to do. All right? So we have to multiply this term times that term, and then this term times this other term, and then this second black term has to multiply by each of the red terms as well. So we get these 4 terms here. Now I'm going to group things together a little bit differently. Notice this I squared. Well, we know that that's just -1, and so this part is actually a real number. And so I'm going to group the 2 real parts, this and this. And you can see that here. And then these 2 parts are imaginary because they have eyes, and so I'm going to group these 2 over here. Alright, now the last step here is not going to make sense to those of you that haven't been in the slightly accelerated program. Those of you that haven't been studying Chapter 9 aren't going to understand this, but don't worry about it. There's something called the addition and subtraction identities for cosine and sine, and they allow us to change from this into this. Now if you take a look at this, it looks complicated, but to multiply, we multiply the moduli and we add the angles. So that's kind of the little catchphrase to help us to remember how to do this. To multiply z1 times z2, we multiply the modulus of z1 times the modulus of z2, and then the angle that we stick in for sine and for cosine is just the sum of the 2 original angles, theta 1 and theta 2. Now you don't have to remember how to make that proof, okay? That was just to show you where this came from. Do remember how to use the formula in the box here. Division, well, it works out to be very, very similar. Instead of multiplying the moduli, you divide the moduli. And instead of adding the angles, you subtract them. I'm not going to show you the derivation, it's very similar, but here's the end result. Now let's practice using these. Here's example 4 from section 10.3. Let's suppose we have 2 complex numbers, z1 and z2, and we want to multiply them. Well, the rule is that we multiply the moduli, so that's what I'm doing here. 2 times 3 gives us a modulus of 6. And to find the angle in the final result, we'll have to add the original angles. Well, they don't have the same denominator, as you can see here, so I have to find a common denominator, and it turns out to be 12. So the angle that we want is 31 pi over 12. Well, it's not pretty, but we're done. All we have to do is stick in the modulus here, and the angle here and here. And that's our answer. That is z1 times z2. Example 5 is very similar, only we're doing division. You can see that I've divided the moduli here, and I've subtracted the angles here and here. Again, I need to play the common denominator game, and I get my final answer here. Alright, now I'm going to take us a little bit further out on the limb here. This is sort of extra stuff on this page, so if you don't get it, don't sweat it, but it is very interesting, I think. I can't prove to you now why, but it is a fact that e to the I theta is the same as the cosine of theta plus I times the sine of theta. This was proved first by a brilliant mathematician named Euler, and in order to prove it you need to learn something about what's called Taylor expansions of functions like cosine and sine and e to the x. Anyway, hopefully in calculus or sometime in university you'll learn about how to do that. Anyway, if we take Euler's equation as a given, well, we can see how it might be able to be applied to the polar form of a complex number. If I multiply both sides times r, then I find that a third way to express a complex number would be r times e to the I theta. Okay, and this turns out to be very convenient. As you can see here, it makes the multiplication of 2 complex numbers very, very simple indeed. And the very strangest thing of all, e to the I pi, if we pick our angle theta to be pi, well, that's cosine of pi plus I times the sine of pi. If we work that out, it turns out that that's -1. And so the most amazing fact of my day is that e to the I pi plus 1 is 0. Wow. Here's your homework for this section. If you can't read that last bit, it says 39 to 47 EOO.